Let's continue on talking about reinforcement learning. We'll talk about a few different algorithms now. The first thing to notice is that Q learning does off-policy learning. It learns the value of an optimal policy no matter what it does. And I want you to think about when that can be bad. So let's have a look at this. Let's have a look at an example here. Whoops. What's going on here? So let's go and have a look at the example here. So here is an example of this agent. Right, and even if I do the greedy exploiting at 0%, so it's not going to exploit anything, and I do sort of a million steps, 1, 2, 3, 1, 2, 3. All right, so it's not exploiting at all, it's just going to act randomly. It eventually learns what the optimal policy is. Okay, if we do another million steps, it's going to learn again what the optimal policy is. So remember, this is one where we start on the left-hand side here. We start in the bottom left here. We go up. Then we go careful up, because careful up, although it costs -1, it doesn't act randomly. So now we've got from this top one, so we can't go up here because going up actually is bad, because sometimes randomly it gets stuck in this -100 going across here. So that's the optimal policy for us. And it didn't actually matter. It actually was terrible. It actually acted just randomly, and that was a terrible thing for it to do. But it still knows what the optimal policy is. So if you want to just act in the world and you want to not get rewards later, then it's a good thing to do. However, if you want to get rewards while you're acting, this turns out to be a terrible thing to do. Because if you look at what the optimal policy is, the optimal policy is to go up into this middle left algorithm. But if you're exploring, this middle left square is a terrible place to be. Because if you're exploring, you're going to randomly explore, you're going to go to this -82.04. So it says that if you're exploring, going to this position is actually really bad. So lots of examples of so-called cliffs, about where you want to walk really close to a cliff because it's the best thing to do, except if you're on a cliff and you explore, it's very dangerous. And that's what this is meant, that's what this was designed to do. So instead of trying to learn the optimal policy, it turns out it's a good idea to try to learn the policy that the agent is following. Okay, so instead of trying to learn the optimal policy, we're going to learn the policy that the agent is doing. And that's called on-policy learning. So let's go back to here. All right. Oh, it starts again. All right. So what we're going to do is we're going to go back to here. And we're going to go... And so what we're doing... And so this can be bad if the exploration policy is dangerous. So off-policy learning is bad if you get judged while you're exploring, and exploration is dangerous. So one policy learns the value of the policy being followed. For example, one is act greedily 80% of the time and act randomly 20% of the time. Okay, so what you'd like to do is you'd like to do that. And the reason why you want to do on policy learning is because it's the policy that you're going to do. So that's actually the one you want to optimize. You don't want to find the best policy. You want to find the policy that the agent's actually carrying out. Okay, so that's why we're going to do it this way. All right. So if the agent's going to explore, it may be better to optimize the actual policy that it's going to do. And so what we're going to look at now is an algorithm called SARSA, which takes the current state, the action, the reward, the following state, and the following action. Because that following action, remember we had to update the Q of S and A, we had to do the expectation of S followed by the following A. Well, A prime is the action you're going to do. So we're going to use that experience to update Q of S and A, and it's called SARSA because it takes SAR, S and A. So that's SARSA, to update Q of S and A. So it's because it does this, does that Q. All right. All right, so let's now look at this. Let's look at the next page here. So here is our algorithm for SARSA. So this is slightly different to the other ones we're doing. So we initialize Q of SA arbitrarily as we did before. Sometimes you might initial it high in case we want to do, pretend that all the good states are good. We can observe the current state. We're going to select an action. Then we're going to carry out the action. We're going to reserve the reward in the state S prime. Then we're going to select the next action, but using a policy based on Q. So now we know what S, A, R, S, and S prime and A prime are. So I can just do our simple backup in this case. Okay, so it goes as Q of A because we know it's Q of S of A plus this discounted, this error term, which is our future predicted value minus the last value, picking it up. Okay, that algorithm is called SARSA. It takes into account both the next state in here. So if we go back to our, the application we're looking at before, the applet viewer, we can reset this. So now we're going to exploit 80% of the time. Right, we're going to use SARSA. We're going to reset this. We're going to step this. And it finds out the best policy here is to actually go right. And you'll notice one other thing here is that the values are all less than they were before. The values have to be less than they are before, because when the values here are not the values of the optimal policy, but the values of the policy that that you get if you actually follow this exploration policy. So if you do step here, there's 10 billion steps we did. And so the price value is to avoid that cliff, and you go around that other point there. Okay, so that's a way of making sure that this is called on-policy learning. So it takes into account what it is you're going to do. And you notice that because it's optimized the actions, you get a higher reward here for following this policy than you would if you were doing Q learning. So if we increase the greedy exploit to 95%, then what's going to happen is that it might be the case as you get greedy exploit gets more and more, it gets safer and safer to go straight up. So it looks like 95% is not good enough. And the trouble is, as you get higher and higher, less exploration, you're not going to find the optimal policy. So as we try and go here, we're going to find out that after a while with greedy exploit, we have this problem is that although we might be the case that it might be the optimal policy to go up, we're not going to find it because we're not exploring enough. So that's what's going to happen here. So if we do this, we'll find out that we're going to wander around. We're going to find out the optimal policy here is to actually still go right. Okay, if I reset this and I do another 10 million steps, I think this is actually the optimal policy with exploiting 99% of the time. So that means it's not exploring very much. The top one's actually quite much safer. Okay, so it's more safe to go into this middle corner here because exploration is not bad, but still going to go up carefully here. Notice the values are all here. They're more than they would be if there was greedy exploit of 90%. And as you get closer and closer to 100%, you're getting closer and closer to Q learning, except the fact that it's might not explore enough to actually find it. Okay, so that's the idea of on-policy versus off-policy learning. Okay, so let's go back to here. Oh, it goes back to the start again. All right. Sorry, I've just got to find the slide again. All right, so that's SARSA. So here's another algorithm that might be useful. We're going to start with action replay. And what we're going to do is we're going to have a set of all previous experiences. We're going to observe the current state S and select action A, and we're going to carry out an action A. We're going to reserve the reward in the R and the S prime. So that's all the same as before. So repeating the other, carrying at A and reserving it. And now we're going to remember that we're at S, A, R and S of A prime. Then what's going to happen is we're going to update Q of S of A as before. We're going to update that. And then we're going to repeat from the experience replay, we're going to increase Q. And so this actually has, so then we're going to do it again for elements of the previous experiences. And what this does, it has two folds. What it does is it sort of lets us mix up more random sampling from experiences instead of always optimizing for the last experiences we're doing. It's going to do that, but also lets us do more interesting backups than before because it actually lets us do, backup. It also lets us do lots of work between observations. So if the action is expensive, we could actually just repeat for a while in the middle. Might be actually as long as possible. We can just wait until we carry out this out. So action replay is sort of something that's very commonly used in algorithms these days. But it's basically the same algorithm before. It's just that we don't only do the experience we've done, but we have ones we've already previously done. Okay, here's another algorithm for us. So what we're going to do is model-based reinforcement learning. So this uses the experience in a much more effective manner. So instead of sort of using an experience and throwing it away as in Q learning, or just basically just using experiences in some, as we did in the previous one with action replay, it's actually going to just learn the probabilities. So it's going to make more effective use of the experiences. It's used really when collecting experiences is expensive. So at a robot or an online game, you have time to do lots of computation between each experience, and you don't want to throw that away. So if there are games that you can just play by yourself without having to interact with the environment, you can do something like Q learning or variants of that. Okay. So the idea is we're going to do is to learn the Markov decision process and interact our acting and planning. So we're going to do interlace acting and planning and learning. So after each experience, we're going to update the probability and the reward, and then we're going to do some steps of asynchronous value iteration. So here's the algorithm now. We've got a few more data structures. We're going to not only learn Q of S of A, but T of S, A, and S, which is a transition function. I was in state A, in state S, I did action A, and the third argument is a resulting state. That's another array. There's an array of the number of times we visited S and A, which is going to be C of S and A, and that's going to be useful for getting averages. And the reward, the total reward we're going to get from having S in state A. Okay, so that's the data structures we're going to do. We're going to remember Q, we're going to remember this transition function, we're going to remember the number of times you did S and A because that's what's going to normalize the probabilities, and we're also going to use the reward. So we're going to assign Q and R arbitrarily. So we can just update those. We also want the counts and the transition probabilities to be 0. You probably might as well just... The reason why I could have R arbitrarily is because you'd add some prior to it. Q, we're going to use that because we might want to do something, have optimism in the face of uncertainty. So the algorithm here has the same structure as before. So we're going to observe the current state. Excuse me. They're going to repeat forever. We're going to select and carry an action A. We're going to observe the reward R on the state S prime. So that's exactly as we normally do it. Okay. And then what we're going to do is we're going to update all of our statistics. We're going to update T as the number of times we visited, the number of times we were in state S and did A and ended up in S prime. We're going to add 1 to that because we have one more experience. We're going to update the count of the number of times we were in S and A, and we're going to add 1 to that. And then we're going to have the reward. We're going to update the reward according to the way we did averaging before. So this actually corresponds exactly to the way we did averaging before. Okay, so we're going to update the reward. Now we got the average reward. So now we can do some steps of asynchronous value iteration. So basically now we're going to do exactly asynchronous value iteration. We're going to select a state and an action. And this is just the previous thing we had before for asynchronous value iteration. We're going to select a state and a reward, but it's now using the counts. So it's now using T of S divided by T of S1A1 S2 divided by C1 of S1A1 is exactly the probability of S2 given S1 and A1. And we also have the mux of the probability of Q. Okay. One of the things you have to worry about in this case is you have to worry about dividing by 0 error, and that's sort of why we might want to start with counts. We want to start with either selecting states and actions we've seen before, or maybe have some other pseudo counts. There's a problem in the bottom here. We have to make sure we don't do a divide by 0 error. But this requires much more data structures, but it's much more effective with the use of data. Okay, so the problem that goes that is it can get divide by 0 error. Okay, let's stop for now, and please ask questions on Piazza. Thank you all.